Hello, welcome to the video lectures of the course Operating System. This is an undergraduate level course which will be covered in approximately 34 to 36 lectures. Supplementing this course will be the tutorials, lab exercises and homework assignments that we will be providing on the course webpage. The link to the course webpage has been provided in the description of this video. Please visit the course webpage, download the tutorials, the labs and the assignments and do them as we progress in the course. They will build your foundations for the concepts that will be discussed in the theoretical lectures. In addition to the tutorials and assignments provided in the course webpage, we have also provided a lab page where we have some assignments that will be provided based on primarily the Linux operating system, some very common programming assignments covering the topics in the course. At the same time, we also would like to give a feel of an actual operating system, and that is why we chose XV6, which is Unix version 6, developed primarily for teaching purposes. We will be using this operating system to understand some implementations of the kernel. Okay, so the course will primarily cover 6 modules, and we'll start off with, starting from today, we'll be initiating module 1, which is a basic introduction and overview of the operating system, and we'll discuss about some very fundamental concepts that will be the basic building blocks of the concepts to be discussed later on. Module 2 and 3 will primarily be related to process management. We'll talk about processes, threads, and how processes communicate and the synchronization mechanisms. Module 4 will be related to memory management techniques involving paging, segmentation, etc. Module 5 will be dealing with file management, and Module 6 will cover some advanced topics such as distributed system, and we'll see some security concerns while learning about the operating system. So let's get started. In the first lecture, we'll primarily be talking about some fundamental concepts in operating system. And the best way to start off this lecture is by defining an operating system. So we would like to know what is an operating system. Now that's a very common question, and if you ask this question to multiple people, they will give you different answers. Say for example, if I ask somebody who likes to listen to music, so he will give you an answer that, okay, operating system is something that allows me to open my music player and listen to the music. Somebody else may answer it in this way, that okay, it allows me to browse the internet on my mobile phone. Somebody may say, okay, operating system is something that allows me to work with the spreadsheet. I can do some computations. Or maybe some say, I like to document something, so it allows me to open up an editor of my choice, without which I can't run my editor. So whatever be the reason why people choose to use operating system, one thing is clear, that an OS or an operating system is something that allows other applications which the users normally use for their different work to run it on a computer system with ease. So that is the main requirement. That is, it allows other applications to conveniently run on a computer system. Okay, so we can put it in this way, that it is a software that allows the user applications to run on a computer system efficiently. Okay, so it's also kind of a software, except that its role is different. It allows others to run on the computer system efficiently. Now, how does it perform this, or what do you mean by efficiently? In order to understand or appreciate the role played by OS in running other applications, let's go a bit deeper and understand how applications actually run on a computer system. Okay, so we would like to know how apps run on a computer system. Okay, so first let's try to understand what is an application. So an application, or we can call it an user application, okay, developed for some purpose. So say an application developed for some purpose, what is it? It's nothing but a set of programs, right? It may be a single program or it may be a group of programs that is intended for a certain purpose. Say a text editor, or a music player, or a movie player, or a browser. All these are a group of programs which have been written to perform a certain kind of a task. Right? So these are typically user applications. Okay. Now what is a program then? A program is a set of instructions. Okay, so it's a set of instructions. Whose instructions? Instructions of a particular machine on which you would like that program to be executed. Okay, what is that machine called? That's what we are referring to as the computer system. So it's a machine that is instructed to perform certain tasks. Okay, so you would like something to be done by that particular machine, you have to instruct it. How? So every machine or every computer has a set of instructions. That's typical of every machine. So the designer of that particular machine, while developing that machine or a computer, he gave us a set of instructions, right? So that is, say, I1, I2, and he said that, okay, I give you n number of instructions for this machine. If you have to write any program, you have to choose it among these n instructions. So whatever task you would like that particular machine to do, from a very simple calculation to a more advanced stuff, you have to use these instructions. That's what it is said. Okay, fine. So if a machine has a certain specific kind of instructions, so a program, what it does is, it chooses from the set of instructions, right? So suppose you have n instructions, so there's a program P. What you have to do is, you choose some I1 to Ik, a set of this from these n number of instructions. So you will be writing your program using these instructions. How do you write a program? So you take these instructions and you arrange them in a certain order, depending on how you want these instructions to be executed. Who should come first, who should come later, in this way. You arrange them in a certain order, and that's how you build your program. Now, when you write these instructions, there are two ways in which you can write the instruction. Either you prefer the instructions written in the same way as provided by the designer of the machine. That is, the raw instructions, the one that came along with the machine, you wrote your program using them, right? So you call that an assembly level or a low level program, where you prefer instructions written in the actual form provided by the machine designer. The other way around could be, the assembly program is a bit difficult to handle because you need an expert to write those programs, and they are, you need to have a detailed information about the machine, only then you can write these programs. Right? The other suitable way could be that you write the program in your own language, okay, or a more suitable language that you feel comfortable with. We call that as a high-level language. There are a lot of high-level languages that have been developed over the years, C, Java, etc. You write your program in these languages and then choose a suitable translator for that language, which will translate that instructions into the instructions known to the machine. That is the assembly language program. So the high-level language would translate that, and the translator is called compiler. Okay. So either of the two ways you can code your program. We'll primarily be sticking to this method, and we'll be assuming that all our codes have been written in high-level language, and there is a suitable compiler that has translated that into a set of instructions known to the machine, and then we'll be proceeding further. So with this view of how you can develop programs, the next step is, remember the question that we want to know how apps run on a program. So the next question is, okay, once you have developed the program, what next? So the next step in program execution is, so now that you have got these instructions, the next step would be that there is a storage location associated with this computing machine. Okay? So this is your computer which is supposed to execute this program. But how will the computer execute this program? It is only possible if you load this program into a storage location called memory. So what is memory? This is an array of locations, array of storage locations. Okay? So you can view memory as a number of locations arranged in a contiguous way. And every such location is identified by something called an address. So let's say this location has an address called x, this is x plus 1, x plus 2 in this way. So these are all addresses of the memory. So if a program has been written, the first thing that needs to be done is the program has to be loaded into the memory. Okay. So if there are a certain set of instructions written which consist of a program, this entire set should be loaded into the memory. So this will be loaded into the memory. Where will that loading be? How will that loading be done? We'll discuss that in the subsequent lectures. So let us say you load that manually or automated, that is the compiler will do it for you, whatever be the reason. So this has to load. So once these instructions will load, every instruction will occupy certain locations in the memory. That means some locations will be occupied by this program. Okay. At the range of locations which this particular set of instructions or program stores or loads into the memory is what you call the address space of the program. So the one that I have shown as a shaded part, let's say these instructions occupy this amount of space in memory. That means this range of address starting from x to, let's say, some x plus k, that is the range of addresses which forms the address space of memory. Sorry, address space of the program. Right? Okay. So once the program gets loaded, the next step is the processor, which is the computing unit of the computer system, has to execute that. So in order to execute that, the computer has to know where does the program start from, which location of the memory does the program start from. Okay. So here in this case it starts from x. So somehow we have to instruct the computer to start executing programs from x. And there is a special kind of a location in the computer as well, which is called program counter. Right? So this is called a program counter. And what is this program counter? Program counter is also a storage location present within the computer that holds the address of the instruction that has to be executed now. So suppose the instruction that I want to execute is x, the content of program counter should be x. So during the loading of the program, once the program gets loaded, there's one more thing that is done. the first location of this program is loaded into the program counter, so that the computer knows where do I start the execution of the program from. Which means it's like a pointer that gets pointed to this particular location, and eventually when this location has been pointed to, the next step that the computer does is it fetches this. That is, it gets the content of that particular location into itself. And there are suitable ways and connections through which this data is brought into the computer. And once it is there, there are different other units that take this data and execute on that. We call that arithmetic logic unit and other storage locations, etc. So the idea is you point to a certain location, get the contents from there, interpret the meaning of that and execute. So in short we can say, so there are two phases which this computer does. One is it fetches something from the memory and executes. So let's the content of X was fetched, it was executed, and then it went on to fetch the next one, which is X plus 1, executed, X plus 2, executed. And how is this happening? Gradually as fetching of X is done and execution is over, it updates, the PC updates to X plus 1, then to X plus 2. So in this way, things go on until you reach the last instruction, which is X plus K, which is fetched, executed, and then the program terminates. Okay. So this is how your applications run on a machine. Okay. Fine. So let us call this kind of model as the bare machine model. Okay. So that is, if you have something to be executed, you have this memory here and you have this CPU. So now if you want something to be executed, you load it in a suitable range of memory locations, right? And that's your program P, and then CPU executes, fetches and executes, and this is how it works. So that's how applications run. That's a traditional way of executing instructions. Okay. But this particular model, this bare machine model, has its own challenges. Okay. So what are the challenges that this kind of model faces? The first challenge that this model faces is, now as long as you have a code that needs to be executed totally on the CPU, you don't have a problem. But the moment your program requires access of some other hardware. What is this other hardware? There can be several I/O devices, right, which can be connected. So this program also needs some kind of I/O access. Say you require some file. Suppose there is a program where a program that wants to, say, print something, or let's say it wants to access some file. Okay. So in that case, the standard procedure of execution, what it has to do, it has to understand which particular device am I going to access, right? And every device that needs to be accessed has a set of codes for its access. Okay. So suppose there is an I/O device 1. In order to access this, you need to specify that particular code which would be able to access this. Okay. So if you follow the normal process of computing, this additional code of accessing this should now be part of your program. So this code, let's say, is meant for access of this I/O. So for example, in this printer, there is a piece of code that actually prints the characters that you have passed here. So this additional code should also now be part of the program. What does this mean? It means that the application must be aware of the details of the hardware that needs to be accessed. Isn't it? Until you know the details of that, you cannot write the code for accessing it. Okay? But these devices can be many. There can be n number of devices. So if you would like your program to access multiple devices, the application must be aware of all the programming techniques of all the devices that will be used. And that's very tedious. Tedious for the programmer, because the programmer has to know all the details, only then he can add that particular code. Okay, so this code will be there for multiple devices, and the application will become bulkier, right? Because see, this is the program. However, if you add this code, it becomes bulky. If you keep on adding the codes for the I/O access, the program becomes very bulky. So that's not a good thing to do. Okay. The second problem is that multiple applications would use the same code for the I/O access, isn't it? So if I am running two processes, say I am running two processes, this is P1 and this is say P2. Okay, this is say P2. Now P2 also requires this access. So the same code will be again replicated here. So this is for the IO1, this is for the IO2. So that's redundant because both of them are accessing the same code. They are using the same code. So a better approach to avoid this problem would have been that these IO access codes would be provided as a utility. That is, what do I mean by that? I mean that a better solution would be that all the IO access codes be bundled and provided as utility. Okay. So it's something like this, that if I have n number of devices and for each of them I have a separate access mechanism, that access mechanism, instead of making that part of my process, the processes P1 and P2 now will not contain that code. Rather, the mechanism to access that will be provided in a separate bundle. Okay, say this is for IO mechanism 1, this is for IO mechanism 2, something of this type. There are n number of devices, IO mechanism n, and I call this entire bundle as a special software. Okay, and I call this as something known as my operating system. So this is the special bundle of software that has them. That can be a very good way to overcome this challenge. Now, how will this work? Now, this will work in this way, that whenever a process P1 would need certain access of a particular device, instead of accessing it from its own space, it would get it from this bundle, right? Suppose it needs IO1, it gets it from here. P2 needs something else, it gets it from here. And in this way, it can execute. So it serves a dual purpose. Number one, the process doesn't have to have the code of the IO access. It's available as a separate software, as a bundle. And number two, because every process would like to execute the same piece of code, it can be shared among a number of processes. Right? And we can decide on how to share. That I'll talk about when I come to the OS goals. But this is the basic idea, that you, instead of providing them as separate codes, you provide them as a utility, which will be shared among a number of processes. So here's the challenge that a normal, traditional or bare machine model would face. And this is one solution, possible solution to overcome it. There can be a third solution, because we say that okay, now these devices, these device codes will be shared among number of processes. So if more than one process you intend to execute on the CPU, there is every possibility that these processes would share something among themselves. What would they share? The different computer resources, memory, files, etc. So whenever you have processes which start sharing, there must be some mechanism to decide which process will be allowed to access that particular resource at a certain point of time. So the moment you have resource sharing, you need management, okay, to decide which process will get the share of that particular resource. Okay, so that's a very important challenge, specifically for multi-programming environments. And the fourth challenge that one would face is when you have multiple processes that would be executing on the CPU. Now it may so happen that a process is currently executing and then it gives way to another process. But if you do not isolate these processes, that you do not have a clear boundary between the area in which these processes can execute, then you may cause trouble. That is, a process, that is a program, may encroach on another program. Okay. That's a very common problem, because program is identified by a set of address locations. So suppose some of the address locations during the execution of P2, by somehow you go into the address range of P1, which is a different program, and you do some tweaking there and the P1 program gets corrupted. That's every possible. That's not so much of a trouble if you happen to change any one of these I/O mechanism codes. Then you have a serial problem. Then that particular device cannot be accessed altogether. So you should not have that. So these are the specific challenges that we face, right? And now, once we are aware of these challenges, here comes the solution to this problem, and that is where OS plays a role. So now we have a special kind of a software which would try to overcome this challenge. Okay, so let's talk about why do we need an OS. Now that we have understood the challenges faced by during execution of a program in a bare machine model, that is a machine where you do not have an OS. Now it's time to appreciate the role played by OS. What is the role played by OS? The first one that OS brings about is the concept of abstraction. We just saw this. What is it? It's hiding the details. Hide the details of the underlying hardware from the user application. That's a very, very useful thing to do. Okay, that is, if you have a hardware resource, hardware means I mean all the resources available to a computer system. That is the CPU, the memory, the files, etc. So if a certain user application, if it wants to access a particular hardware, it doesn't have to know the details of the hardware. It doesn't need to know. Okay. So a user application, if it wants to run a certain hardware, if it wants to access certain hardware, doesn't have to include that particular I/O or hardware access mechanism. Rather, there is a second layer sitting in between them, which is called the operating system, which you can view as kind of a bundle of such I/O access codes provided as utilities to the applications. So the applications now do not directly access the hardware, they request that for that particular I/O access or hardware access. The OS understands or interprets that particular request and in turn executes that I/O access or hardware access instead of the application. And once it gets back the result, it sends it back to the application. So this is how it works. In form of a memory image, it's something like this. That assume that you have a process which is occupying some memory, and here is the bundle of utilities. You call that as the OS, and this OS has a number of such kind of codes for performing access of different IOs. Whenever a certain program wants to access one of them, say for example, let us go back to that printf statement. So now that this printf statement, which is part of a particular program, so this is the printf statement, what does it intend to do? It intends to print some characters, where in some output device. But that output device is not directly accessible to that particular program. Okay. So what happens is, the program, it puts a request to this piece of software called OS. So this request is put. How do you put this request? This request is put in the form of some function calls. So this is the interface, right? So this is the mechanism through which you can put your request. There are some list of functions. You apply that particular function in your code, and the moment that particular function is accessed, now the OS understands that this is the piece of code that I should execute. Okay, and then the OS executes that particular IO access code, and whatever be the result, it sends it back to the program. So this printf statement is actually transformed into something called a write. So that's a function called write. So these function calls, we don't call them function calls, rather we give them a special name called system calls. Right? Why are they called system calls? Because they are function calls. However, they are requests made to the operating system that please execute this code for me. Right? I'm not going to execute that. Please execute the code for me. I am putting a request to you. Now, looking at that particular request, that is the system call, the OS identifies that which system call or which particular IO or which particular hardware is this request for, and accordingly it looks up into, it maintains some kind of a data structure, a table kind of a structure where it looks up, finds out which particular code should it execute, and execute that for the application. Okay, so this is how the OS ensures abstraction. The summary is that it does not execute, the processes do not execute the hardware, do not access the hardware, or they do not access, do not execute the IO access code. Rather, this is done by the operating system, which is nothing but a bundle of utilities of these kind of services. And the program puts a request to the operating system for doing that, and the operating system does it and sends the result back to the application. So the OS then sends it back. So this is how. So this is the system called request, and this is the result of the system. More about the system calls we'll discuss in the next lecture. So this is kind of an abstraction. The next interesting thing that the OS does is resource management. So that is the second goal. We saw that when a number of resources share among multiple programs, it's essential that they have to be managed, the sharing has to be managed. And operating system does that by a technique known as virtualization. As the name implies, it virtualizes resources and provides a virtual copy to each one of those participating programs, so that the programs, they believe that each one of them have a copy of that particular resource. However, the resources are actually shared among processes. So this is the trick that the operating system plays with the processes. So let me give an example. So we'll talk about two virtualization techniques. The first is virtualizing CPUs or processors. How does the OS virtualizes CPUs? So think about a situation where you have two processes, P1 and P2. And there can be a situation where P1 is currently being executed on the processor. Right? So CPU is executing the instructions of P1. Now during execution, suddenly there is a particular instruction, something of this printf type, which is nothing but an IO access instruction. Okay? You would like that some resource to be accessed. And we just saw that the program doesn't execute that. The program doesn't have the privilege to access the hardware. Rather, it's the operating system that does it for the program. And how? The program puts a request and the operating system does it. Okay. So what happens to the program during this time? If you look at the execution cycle of a particular program, you will find that for certain instant of time, the program was, so this is time axis and this is maybe P1 which was executing, and I'm showing you the execution cycle of a process P1 on a CPU. So for this amount of time, let's say the P1 was executing on the CPU, suddenly it hit upon this kind of instruction, which means that it is request an IO, and we just saw that if this IO request has to be made, it has to be done by the kernel. The program doesn't execute that. So what happens to the program during this time? It waits. Okay, it waits. What does it wait for? That particular device to be accessed and whatever it needs to be done to be completed. Okay, and if you look at the entire cycle, there are multiple such instances at which the process P1 or the program P1 has to wait. But then that's not a good thing to do because it brings down the performance of a system. So a better approach would be that during the time when P1 was waiting, why don't you allow some other process to get executed on the CPU so that you don't waste CPU cycles? So let's say there's a process P2 which is also there in the memory. So why to keep that waiting until P1 completes? Better, when P1 is hitting up on this printf, you take that out, right? You take it or you call it, you swap that out and you bring P2 to start executing this. So the moment it hits upon this, you stop the execution of P1 and you bring the execution, you bring P2 into CPU. So CPU now starts executing instructions of P2. Okay, and after some time, P2 may also require some IO access. Good, then P2 will also go into some wait state. And during the wait state of P2, if there is some other process called P3 waiting, you can allow that to be get executed. Or maybe P1 has completed its IO wait for that amount of time, that is its printf statement, whatever it wants to do, is over, then you can allow P1 to resume. So in this time sharing fashion, okay, so in this time sharing way, we can allow processes to be or programs to be executed in an interleaved way. They don't have to wait. And multiple processes can be or multiple programs can be executed at the same time. And if this execution time or this switching time is very fast, then the processes or the programs, they feel that they are running for their entire duration on the CPU. They don't understand that they were taken out and the other processes were executed during this time. Okay. This is the virtualization. It feels as if the OS has taken that single CPU, let's say the computer system has a single CPU, it as if creates a virtual view of two CPUs and provides them to each one of the two processes or the programs. So the program believes that the entire CPU was with me and I was running on that only. So that's how we can say an OS makes these programs believe that they're using the entire CPU. That's virtualization. We have already given you a program called cpu.c in the tutorial section. Please refer to that, execute that, and see for yourself how multiple programs, when they get executed, it seems that these programs are running simultaneously. However, there's a time sharing that is done. So please utilize the tutorial for better understanding. Now, along with that's one way in which OS virtualizes. It also virtualizes the memory, and this is a very interesting thing because it actually helps in a lot of ways. What is this? What is memory virtualization? The operating system actually creates a virtual view of a program. We know that program is a set of instructions which occupies certain range of addresses in the memory. Okay, that's what is known to us. So let's say this is the range of addresses that the particular program, say P, it occupies. But what OS does is it creates one more view of this program, and this view is called a virtual view, a virtual address map. Okay. Now, why is this necessary? This is necessary because in some situations you may have this program loaded onto the memory in a distributed fashion. What I mean is that this program, as you see here, you may feel that this program is loaded always in a the program sits in a memory in a contiguous fashion. That is, the entire program is sitting in locations one after the other. But that's not what should be done. Why? Because you would like your program to be executed in chunks. Okay? Program, if you see, is a set of instructions which the CPU wants to execute. But not all instructions have to be executed at the same time. They execute one after the other. So some part of a program when it is running, the other part is not executed. So if you can bring this particular program in chunks, okay, say you have a 4 MB size program, you don't load the entire program at one go. You load only, let's say, some 2 MB. Okay. Some 2 MB size memory or of a program you choose. This is only 2 MB. You will load the rest of the 2 MB later on. What do you achieve by that? You achieve and you create an additional space for storing other programs. So let's say this is program P1 which is currently loaded here, the 2 MB. The rest of the 2 MB is we are going to bring next. The other space, that is the rest of this, can be allowed for storing other programs, let's say P2. Okay? And for P3, P4, so you can allow other programs to also reside at the same time along with P1. Had this P1 occupied entire 4 MB, you may not have got that amount of space. So it's a very good ploy that you bring them in chunks and you allow them to be loaded. Now the question is, when this next 2 MB comes, where will that sit? Wherever it gets a free place, it will sit there. So maybe this is the place where your next P1 chunk sits. This is 2 MB. Okay. You can sit. So this is how it's a distributed way of storing your programs in memory. But there's a problem here. The problem is that if you want to access these program chunks, okay, then the CPU has to know which chunk is sitting where. And because it's totally distributed, it's very difficult for the CPU to maintain that. That's a problem on the side of the CPU. Okay. So what is to be done? Our technique could be that, okay, let this chunks sit in the physical memory as they are, but we'll create a virtual view of that, which will be contiguous. And this entire 0 to, let's say, 4 MB, this this entire 4 MB is the process size or the program size. That's contiguous. And interestingly, the CPU will see this view and not this. So whatever instructions it would like to execute, it will generate their request for those instructions keeping in mind this particular view. So say there's a certain instruction that it wants to execute for this location of this particular virtual address map. Okay. Now this location that it wants may be here or may be here, either of the two. But CPU doesn't need to know what exactly where this particular location is. It looks at this and sends it. So even if they change positions later on, the CPU doesn't want to bother. It just wants this location. So that's a very, very advantageous way to handle this situation. But if you have two views, there must be some kind of a mapping between the two. Who maintains that? So that is what is the role played by the operating system. So what we find here is, for any addresses that are being generated by the CPU, keeping in mind a virtual address map, they are also sent to the OS. And the OS interprets them. So this address that has been sent is a virtual address, you can say, or we often call it logical address, virtual address or logical address, because it's not the actual physical location of the instruction. Okay, so it sends this instruction for a virtual address, and this virtual address is interpreted by the OS. The OS knows that this location in the virtual address corresponds to which physical address, whether it is in this chunk or this chunk, and accordingly either it sends it to access this, it knows which location, and then it sends it to this. So this is how the OS manages a distributed form of storage of a program in the physical memory, whereas it doesn't, the CPU doesn't have to know the details of the actual location of a particular program. It generates instructions keeping in mind the virtual view of the particular program, and accordingly the translation is done by the OS. So that's the first advantage, that virtualizing memory ensures that the programs can be distributed throughout a physical memory. Okay, and it allows the programs to be loaded in chunks. So even if your program, which is of a size 4 MB, doesn't fit into your memory, there's no problem, because you can bring them in chunks, and the chunk size that you would like to be loaded into the memory depends on what amount of space you have for that particular program at that particular moment. So that is the basic idea of virtualizing. Okay, so it feels that the program, the CPU feels that the program, the entire memory has been allocated to that particular program. However, it's not, it's only certain part of a program that is there, which is residing in the private memory or the physical memory. So this is the concept of a virtual address or virtual memory. Okay. So this is the second goal that we discussed about the OS. Now, the third goal that the OS, the third goal of the OS is to bring about something called isolation. So recap that when we were discussing about the challenges, we said that there is, when you deal with multiple programs in your system, there is possibility that one program may encroach the space of the other, and that may disturb the other process. So you do not want that to happen. And what is the solution for that? You keep a check on the amount of address in which a particular process can execute or a program can execute. Okay. So what we intend to do is we intend to perform something called a dual mode of operation. What is this dual mode of operation? We clearly demarcate the range of addresses where the OS code can execute and the user code can execute, or the user processes can execute. So if you look at the memory, you find that some range of addresses you earmark for the OS, and the other range of addresses you call it the user space. That is where your programs can reside, P1, P2. So your user level programs can reside here, and the other portion you keep for the OS level code. Okay. So now, how do you ensure isolation? We just saw in the abstraction that there are some instructions, okay, such as the IO access, that you have decided that will be executed by the kernel. Okay. So among the number of instructions that you have decided of a machine, so the machine instructions that we have decided, some of them we call privileged. Okay. That means they are special kind of instructions. They have to be executed by the operating system. And then some of them are non-privileged, which will be executed by the user applications. So obviously the privileged applications, privileged instructions will reside in these address ranges specified for the OS, and all others will be executed in this space. Okay. But whose instructions are they? The machine instructions. So as a result, the hardware of the machine should also participate in deciding this privileged and non-privileged. So we have the hardware or the CPU that has a mode bit that decides whether the CPU will be executing privileged instructions or non-privileged. So if the mode bit is 0, it means privileged. And if it is 1, it means non-privileged. So for all instructions which will be executed by the kernel or rather the OS, the first thing that is done is the CPU, it switches itself into a privileged mode. Only then it can execute the privileged instructions. And for the rest of the time, when a user application is running, the CPU remains in the non-privileged mode. Now there's a transition that happens when the user program wants to access some kernel level instruction. Remember that printf statement when we were trying to execute? So let's say there is some user application which would like to execute something. Okay, but that instruction that particular user application wants to execute is a privileged instruction. So the first thing that happens is it makes this request in the form of a system call to the kernel. Okay. So say this is the user space and this is the OS space, the OS instructions. So the application, consider that printf statement, it puts this request to the OS, and at the same time, because the request that has been put to the OS will be executed by the OS, but those instructions are privileged, so the CPU has to switch its mode. So the mode gets switched. So the OS now looks at that particular request, which is the system call. It looks up into the data structure, that is the table which it has maintained, finds out the code that it needs to execute, executes the code. So here you have the OS, it executes the syscall and it returns it back to the app. Okay, now when it does that, the mode, it switches back to it. So this is how you have a dual mode of operation. Okay. Now this dual mode of operation clearly isolates the two range of addresses. One that is executed by the operating system, the other by the user applications. So instructions which should be executed by the operating system cannot be executed by a user application. Okay? Because the user applications do not have a privilege to execute those. It only has to be done by the OS. So what if that particular application wants to execute that? It has to request the do it for that application. And the mechanism to do it is you request that in the form of using an interface which is called a system call, one of the functions among many functions, and that function is interpreted by the kernel or the OS, and the moment it does that, the CPU switches itself and executes that and returns the result back to the application. So this is the dual mode of operation. Okay, so with this we covered a few fundamental concepts related to operating system. So let me quickly summarize. What we covered so far was the basic definition of operating system, which we found as a software that helps other user applications to be executed on a computer system. Then we moved on to discuss about how user applications run on a computer. We found that the user applications have to be developed in the form of a program, which is a set of instructions. Then they have to be loaded onto the memory. The moment the user application gets loaded on the memory, it occupies a certain range of address. And the processor has to be instructed that which is the first address of that particular program. The processor executes each one of them, one location after the other, until it reaches the last. And this is how, through a fetch and execute cycle, the applications run. But we found that there are certain challenges that these programs face while execution. One among them is that in case the program needs some I/O access, then the code becomes bulky, the designer or the programmer has to know the details of that hardware. And then multiple applications, if they would like to access the same hardware, every time they do that, the same piece of code has to be written. Then we found that if the resources have to be shared among processors, then there is a management that needs to be ensured. And the processors, they have to be isolated so that one does not encroach into the other. And we found that operating system actually fits into this role to overcome these challenges. It's kind of, you can say, a bundle of utilities which provides bundle of utilities for providing different services, which are nothing but the I/O accesses. For different I/O devices, you have a specific code for that, and the OS can be considered as a collection of all this. And then it works it in a special way that this particular code can only be executed by the operating system. So it hides the hardware details from that user application. The user applications do not need to know the details of the hardware. It puts a request and the OS executes it. Then we found that the OS execution and the user space execution, they have to be isolated. That is, all instructions that the OS can execute and the user can execute, they cannot be at the same time, or the programs cannot execute the same thing as the one that to be executed by the OS. And how do you ensure that? That's what again is the role played by OS. It tries to isolate the two by having two modes of operation. The CPU flips its operation mode and accordingly executes the different type of instructions. And finally, we also found out that the way in which OS manages the resources is through a concept of virtualization, where it tricks the processes to believe that the resources that are available to them are dedicated to that particular process. However, whether it is CPU or memory, they are virtualized and the processors feel that the entire physical resource is available to them. So that is what are some of the fundamental concepts to begin with in this course. In the next lecture, we will be going a bit deeper and we'll talk about some more fundamental concepts. We'll introduce the concept of processes, then interrupts, and we'll talk about a bit about system calls. So that will form the foundations of the rest of the lectures.